All right, in this last section of Chapter 9, we're going to look at multiple bonds. So here's a molecule of ethene. It's got two carbons right here, a double bond between the two carbons. And if we were to count the hybridization around this carbon, we'd go sp-p. So we'd say it's sp2 hybridized around this carbon. And it would have this linear overlap right here between the carbon and the carbon, between the carbon and the hydrogen and carbon and hydrogen along the internuclear axis that causes those to bond together. And there'd be an amount of orbital overlap that's just right. But what about the second bond? What about this second bond right here? This is a double bond. So we just described like one of the bonds being like linear overlapping. What about this second bond? Or if something had a triple bond, what about the third bond? Well, we're now going to learn about two different kinds of bonds. And they're given Greek letter names just to be fancy because, of course, we do fancy things because we're in chemistry. So the two Greek letter names are sigma, and this is the Greek letter sigma in your book. It looks like this. It looks like a circle with a little umlaut over the top of it, kind of, hanging off the side. And one that you've seen before, a pi bond. Pi, as in the Greek letter pi. That's the second kind of bond that we're going to talk about. So I'm going to move this piece of paper right here. I'm going to put down the two different kinds of bonds. So we have sigma bonds, Greek letter sigma right here, and we have pi bonds, pi bonds, not to be confused with the number pi, but this is just a description using the Greek word pi. All right. So sigma bonds are single bonds. They're linear along the internuclear axis. They're an overlap of two hybridized orbitals, or maybe not hybridized orbitals, but ones that are along the internuclear axis. Pi bonds only happen when there is a second, a double bond, or a triple bond. And that's because it's got to get out of the way of this internuclear axis, a top and bottom overlap. So these are unhybridized p orbitals that overlap over the top and over the bottom of one another to form a second bond. So there's a first bond going right along here along this axis, and then the second bond goes over the top and over the bottom. So these bonds, this pi bond, is unhybridized p orbitals that form this second bond. It's not as strong as a single internuclear axis sigma bond, and it's above and below the axis. Let's give a couple of examples of these. I want to show you the really nice diagrams they have of these in the textbook as well. And let's take a look at, well, here's our one that we just talked about a little bit ago, the ethene. So you can see the internuclear axis right here, and then here's the pi bond that goes above and below right there. That makes the second bond. So the double bond is actually consisting of this sigma single bond right here, and then the top and the bottom right here are the pi bond. You can remember that there's two parts to it because there's two legs to a pi. All right, let's do some examples of these guys right here. Here is a molecule, and inside of this molecule, please identify the number of sigma single bonds and the number of pi double or triple bonds. Well, sigma single, 1, 2, 3, 4, and then one of these would also be a sigma single bond, so there would be 5 sigma single bonds inside of this molecule. These two right here would be above and below the internuclear axis, and we'd have 2 of those pi bonds inside this molecule. All right, what about this guy? Sigma bonds, remember one of the double or one of the triple is always a sigma bond because it bonds right along this internuclear axis right here. So we would have 2 sigma bonds, 1, 2. And then pi bonds would be above and below the internuclear axis, 1 here and 1 here. So there would be 2 pi bonds right there. An interesting molecule to look at for sigma and pi bonds is a resonance structure, and I chose one called benzene because we learned about this one in Chapter 8, where we have this rotating double bond right here throughout the structure. And instead of drawing it 2 different ways and drawing all of these electrons that go in between, they actually drew it as a hexagon like this, and then they put a circle in the middle, and the circle indicated that this double bond rotated from here to here to here to here to here to here, and this rotating double bond was the thing that was illustrated right here. Well, when that happens, we actually take each one of the internuclear axis bonds right here and form a sigma single bond right here. So we have 1, 2, 3, 4, 5, 6 sigma bonds in the central hexagon. So 6 sigmas in the hexagon. And then, of course, we have sigmas on the outside too, so 6 more. And then these double bonds actually delocalize, and these p orbitals overlap with one another right here. And these delocalized parts at one instant look like this, where they bond, bond, bond. The next instant they look like this, where they bond, bond, bond. And they just kind of say it resonates between each other, and so we end up having 3 pi bonds inside of here. 1, 2, 3. You can just count them in the non-resonated form, and you'll see how those work. These delocalizations of electrons allow the electrons to flow between here and cause like a bond and a half for each piece. The delocalized electrons are due to the resonance of the structure. So where does this actually apply in your real life? Well, it actually makes a big difference in something called vision. Yeah, your sight. This is on page 411 of your digital book. And so this is like a zoom in of your eyeball, and on the lens of your eye, it focuses light onto what's called the retina. And on the retina, it contains photoreceptor cells, and there are 2 types. There's ones called rods and cones. And then the rods contain, well, the rods and cones contain a molecule called rhodospin, and inside that there is a protein called opsin. This contains a chemical that's triggered by light. So inside the opsin, we actually have a single and double bond, and you can imagine it being like this. There is a double pi bond going on in there. When the light hits that opsin, what happens is it's strong enough, that photon of light is strong enough to break that double bond. When it breaks that double bond, now this part of the molecule can rotate. That rotation then allows it to trigger the synapse of a nerve and then send a signal to your brain saying, hey, look, this is light. This is causing vision to occur. And so the breaking of this pi bond, but not the breaking of the sigma bond, is critical, because after light goes away, then it rotates back, and eventually the pi bond forms again. And so it's reusable just by breaking the less energetic, or the one that takes less energy to break pi bond, and allowing it to rotate gives you that vision to take place, and allowing the rotation to take place. The eye is so sensitive that it only takes as few as 5 closely spaced molecules reacting in this fashion to produce the sensation of vision. Thus, only 5 photons of light are necessary to stimulate the eye. There is some use for your sigma and pi bonding in the real world. Good luck with your identifying sigma and pi bonds.